Welcome everyone to this week's lecture for hacking in C. Thanks for waiting the 1 minute. I forgot that I had to open up a folder with my examples. So where were we last week? We saw that because code and information that relates to control flow, such as the return address, is all in the same memory as the data that your program manipulates and reads and writes, we can use that to our advantage. And we saw some examples of that input can come from places where we don't expect it, and that if we trust that input, then we might be making mistakes. Usually we are making mistakes if you trust user input. We saw a bunch of things about printf, extending from what we did 2 weeks ago. We saw that we could do arbitrary reads and writes to memory by using %s and writing using %n. And I should there also point out something I forgot to say last week, is that there's also these variants, sprintf, fprintf, and they have all the same problems. Then we went into buffer overflows, mainly that you need to be very careful considering the sizes of buffers. You cannot read from you can read from arbitrary places, so you need to be sure that if you are reading a buffer, it's within the size of the buffer, and then when you write it somewhere, it's actually inside the buffer and you're not overwriting something else. We briefly went into getS. In my attempt to stay up to date with the latest memes, I've tried to add a video to a LaTeX PDF presentation. I was not very successful, so you have to do with the still image, but yeah. getS is still a very, very bad thing, of course. So printf, we saw that, and we can use that to read things. We can also, we saw this piece of code, and if we give this printf function a lot of %x's or something, it'll start reading up the stack, and you should see the data that is in buffer. So we also saw this piece of code where we have the getS function being used, and that if we give this enough information, then we can start to overwrite this whole thing, and we can again use the printf here to also see what is happening. And we saw that that can break things. So if we give it way too many A's, then we will start to overwrite first the frame pointer and then the return address, and that will make your program crash. Of course, the address, an A is in hexadecimal, the number 41, so jumping to 41, 41, 41, 41, 41, etc., that's not very helpful. But what if we feed it something else, like this hexadecimal string? Well, then we will jump to that place in memory. I don't think it's very likely that there's a valid address called bad code in your program, but we could also insert other things, of course. Again, these actual values, 108 is just an example. It might vary a bit with the alignment, sizes of the buffers, all the local variables, etc. So what we're going to be doing this week is based on the fact that we're going to more or less solve the problem that we want to run arbitrary code and not just code that's already part of the program. If you jump to insert a function address, for example, in the place of bad code here, you will jump to that function. That was also exercise 3 of the homework. problem there is that often we don't have exactly a function that does what we want to do, and usually what we want to do is get a shell so we can run arbitrary commands. So typically a program does not contain a function called please give me a root shell, and there's a way around that, and that way is that we will insert our own code that is not part of the program at all, and insert that into the program to spawn a shell. Such a piece of code is called shellcode, and we're going to be making our own shellcode today, but usually you would steal it off a website such as Shellstorm. Remember that code is data and data is code. So by just as that is exactly the same for the CPU as far as it's concerned. The only thing that the CPU cares about is what operation you're trying to do it. If you tell it to interpret code, some string as code, it will try to do that, and vice versa. If you have some code and then make it a string and just inject it somewhere, it'll also happily happen. And that's what we're going to be doing here. So we're going to put our own code into the memory of the program somehow. We need to figure out where we then put it, and then we can jump to that place by overwriting the return address. Obviously, we cannot just input some C source code and expect it to work. That is C is a compiled language, so that C source code will not be evaluated, compiled, and then executed in a way we like. So we'll have to do it with machine code, the bits and the bytes that the CPU can actually read. I will briefly here answer the question that's the alternative to get as string. I think that fget_as should work. Basically, you want something that either allocates its own memory, so it will just give you a buffer on the heap somewhere, and then make that buffer as big as is necessary. Or such a function would need a size limit, so that you can specify what the size is that you expect at most. Okay, launching a shell. If we are writing a C program that launches a shell, we can write something as the following. There's this execve command that is a system call that will execute a program, and it will expect the name of the program as the first argument. Then it expects the arguments to the program, and then there's this null thing, that's the environment variables. Specifically, this is the execve thing. So we have the file name, that is the program that's going to be loaded. Then there's the argv thing, and that's the list of arguments passed to main. That's actually exactly the same contents as the argv list that the main function in a C program gets. So you also need to put the name of the program as the first argument. And then there's env, that is the list of environment variables, specified as key equals value. So with this equal sign in between, and we can just leave that out by specifying null, which is what we did in the last thing. These two lists of environment variables and arguments are a bit like strings. The execve command knows how many there are, not by passing a length, but that the last ones need to be null. The last elements of these lists need to be null pointers. This first argument, again, just like in main, the argv that your main function gets needs to be the name of the executable. A system call is actually a request to the operating system. So you'll learn more about that in the operating systems course. More or less, you're telling the operating system, please launch this program for me. how you such a system call is a special type of CPU instruction. Actually, it's not just a function call. What will happen is that there's this list of system calls that exist, and you put the right arguments in the right places, and then you call the system assembly command, and that will then trigger a special handler where the operating system will kick in and then do the stuff for you. sysexecve is the actual system call that we want to be doing, and 59 is the number of that system call. And we need to put that number into the REX register. Yes. And then the arguments need to follow in the RDI, RSI, and RDX registers. This is how system calls are specified to behave. You put what system call you want to do in RAX, and then the arguments in these other registers. And then as follows, you will call system and it will execute stuff. So this is more or less what we need to do. We need to prepare this in a special way so that we can more or less, we want to run this program, but then sort of manually compile it. So the problem here is that we want to run this execve in our injected code, and the way we're going to inject it is as a string. We need it in machine code, which is why we're going to be writing it as assembly, and then we'll be translating that assembly to machine code. And we cannot just run the C compiler over the program that I just gave you, because the problem is that we want to inject it as a string. And the problem with supplying the C compiler is that it will make the normal choices in instructions, which will involve a bunch of NullBytes in various places. And we will need to write this this code very carefully, such that we can avoid all NullBytes, because otherwise it would just terminate our shellcode halfway through, and we cannot have that. It needs to be a valid string, so everything is okay except NullBytes. So let's set up a to-do list. We need to get a pointer to bin.sh, which is the shell that we want to start, and we want to put that into our first register argument, which will be RDI. Next, we need to create this array of pointers to strings, and we need to give that as the argument for argv in RSI. This needs to be this pointer, the same pointer to bin.sh, or another pointer, but it's more easy to do it the same pointer, and then a null, because this, remember that this list needed to end in a null byte. The address of the second needs to be put in RSI, and then there's this third register for the NFB. We can just set it empty, and to do that we will just set this argument to null. Finally, we need to put the system call number in RAX, and then call the syscall instruction. So null is a bit of a problem. We need a bunch of nulls in this to-do list. We need one here, we need one here, and there's also a null byte at the end of these strings, which we also need to put in memory. So we need to get around those null bytes, because strings are null terminated character arrays. So any null byte in our input string, in our shellcode, will mean that the rest of what follows will not be read. What we will do instead is obtain null through a trick. If you XOR something with itself, it will always become 0, so we will just XOR a register with itself to blank it out. This is one of those things why we need to do this manually, because what a compiler would just do is morph 0 into register, to set something to 0, but that obviously doesn't work, because that 0 will be a null byte. You see where it's going. What this means is that we have one of our to-do list items done. we have set RDX to null, the empty NFP. Next is the bin_h string. The obvious solution would be to put this string on the stack somewhere and then just use the stack pointer. That saves us having to deal with the heap, which is super hard if you're writing assembly code and much more effort than we are willing to put in. So we'll just put it on the stack somewhere and then use the stack pointer address as the pointer to this string. But this string, again, also needs to be null terminated. It still needs to be a valid string. So what we will do in our assembly code is have a little trick. We will write this string bin_h, but then also have an a. This is in little endian, so it's in the reverse. But what we have is bin_h and then an a at the end. Now, why do we need that a? Well, this makes this thing exactly 64 bits, which is the number of bits that an integer can be at most. So then this fits nicely into the memory and won't be encoded with a NullByte somewhere. Then we use this shift right instruction to rotate the OX41 out of the value, because we just shift everything and then this 41 will drop off, and at the end the zeros will be inserted. So what we now have is the bin_sh and then the NullByte at the end, which is what we needed. We have then pushed it onto the stack. So that will set the stack pointer, and then we will get the value of the stack pointer RSP and copy that over into RDI, our first argument. So that means that we have 2 of the 6 items done that we needed to do. So we can follow up to the next one, which is creating this array of pointers to strings. The argv array. We need consecutive memory to hold this pointer to bin_h, and then we need a NullByte. It needs to be consecutive because an array is consecutive, so that needs to be next to each other. We already have null in RDX because we set that with the XOR trick. We have RDI that has the pointer to bin_h. After the rotation is done, etc., that's just still in there. So what we can just do is push these 2 things to the stack. Again, we push values and copy the stack pointer address into RSI, and then that thing is set up correctly. Remember that because the stack goes downwards, we need to push this in reverse order, because while it's being growing from the bottom to the top, we do read downwards, so we need to push this in a reverse order. Hello? Yes. That means that we have these 2 items done in our list. Then all that remains is issuing the system call. We will put the register in our AX and then call syscall. To do so, we will first zero out RAX and then put 59 in the lower part of this register and call syscall. Well, that's our to-do list. We're done. So this is our recipe for the shellcode. Now, we also need to encode that into bytes. There's ways to do that. Usually I try to not put in that effort. But this is the whole assembled shellcode. Now, this might have gone a little quick for you. Fortunately, this is not something you have to reproduce yourself. In fact, I've already given you a program that can print out this exact shellcode and yeah, there's no real reason for you to just not reuse this. It's nice to see, though, that there needs to be these tricks to get around the problems that we have with that we need to get around these NullBytes, etc. And it's a nice way to puzzle about how you can squeeze things and push things on the stack, etc. I've said that I've already given you a program that does that. Oh, that's a bit glitchy. Yes. There's this shellcode.c file, which contains not only the shellcode, but also a variant of that program that calls bin ls. So that's helpful because that a shell that is a bit interactive. It needs input to show you something, and it's not always nice. Whereas if you just execute bin ls, you will get immediate output because it won't wait for you to type something and then respond something back. So I like testing things with bin ls. And then this is a nice program that will automatically print that for you. So if I type make shellcode, then there's this program and it tells you exactly what to do. Shell, that was weird. I think that might be a bug. You'll see that it outputs some garbage here. That is the byte representation of the shellcode, and it probably didn't even print out all of the different things that we saw. But you see that it is more or less exactly the code that I just showed you. And there's also the bin ls list variant, which prints out the same code but with bin ls. You'll see that's exactly the same in all the other places. This program is available to you as well. There's this, where did I hide my, Tom's hacking utilities. Oof, that's bad. Tom's hacking utilities that is listed here, and that's these tools that I wrote last year to do some of these menial repetitive stuff that are a bit annoying to do by hand. It also includes that program that I used to reverse addresses last week. You'll probably find that these tools can be very helpful for you in the next homework and during the exam stuff. Or, well, it's not really an exam, but the graded stuff. So, I will come back to that later today. No worries. So, we have now some code to inject into our program. And that is the first step that we need to do. The next thing that we need to do is getting the program to run our code, which is, of course, kind of the most important part, because if that doesn't happen, then it doesn't matter that we did this first thing, followed by question marks and profit. So let's figure out how we can get this code into a program. We have the shellcode, and what you could do is copy the thing and insert it into some nice file, and then you can just read that file all the time. Or you can write a program such as I did and just run that program. And then inserting that code into the vulnerable program is quite easy. You can just read the file and then provide it as input, etc. We already know that we can take over the stack pointer if there's a buffer overflow, because we can just overwrite it. But what do we overwrite it with? Where is our code at? Well, that is the address of the buffer that getS will read into. So that brings us with the following question: how do we find that buffer? There's obviously some ways to cheat. We can just print it out, edit the program and add a print statement. Not really satisfying. If you use a debugger, you could use the debugger to print out the address and then use that address that you obtained. And another good option is to use a format string vulnerability to find the address. Typically, that's the only option that you have if you're trying to exploit this remotely, and especially if you don't have access to the source code. And then you need to inject this into the program somehow. So what you could do is read the shellcode and then print your address using printf with these double quotes and then these escaped bytes, and then give it to your vulnerable app. Mind the endianness. It's very important to do the endianness correctly when inserting this kind of stuff. And you either will need to use my reverse address tool, or you will need to swap all of the bytes yourself. Often you won't get an exact address of the buffer that you're trying to overflow. And that is something that you might need to work around, because you are likely to find things on the stack, but the exact start of where you inserted your shellcode might be a bit vague. It's somewhere between there and there. Could be a bit annoying. You know it's around this other variable, but yeah. Also, you will know that the frame pointer is somewhere, and that will also give you some idea of the locations on the stack, because you know that, okay, it's going to be somewhere below this thing. To run our shellcode correctly, we need to execute all of the bytes of the machine code that we wrote, because otherwise you will skip one of the steps and it will just crash because you won't specify the arguments to the execve command correctly. So we need to precisely start executing that code at the first byte. Remember, the first byte was this XOR operation, which gave us the null, which we then used in every single other command pretty much. So we need to start precisely there. There are two solutions to overcoming such an imprecise addressing problem. Either you just try out a whole bunch of addresses through trial and error. I would recommend writing a script if you want to do that. But there's also another trick that we can do. We can sort of enlarge this start of the shellcode such that we have a larger point of entry, so to say. Using both is often the best approach, because then you just enlarge the probability of guessing correctly. So what is this entry point? Well, there's this knob instruction. Don't ask me why it's necessary. There's probably a good reason for it, but there is an instruction in your CPU where you can ask it, please don't do anything. No operation knob is encoded as the hexadecimal value 90. And it does simply nothing. So we can just put as many of those as we want, or as we can get away with, just before the shellcode. This is helpful because then we can more or less get a large entry point, and then we can just have this large margin of error. What we can do is the buffer starts somewhere here. We have a whole bunch of knobs, and then we just put them somewhere before the shellcode. And then instead of jumping exactly on this line, we can just jump on any one of these knobs, and it will work more or less, because it will just start here, and then you don't care how many of these knobs you execute, as long as you get to the start of your shellcode and run that all the way through. Such a sequence of knobs is called a knob sled in the jargon, because it allows you to slide into your shellcode. This is also a knob sled, but maybe not as helpful for executing attacks, but I found it funny. So, putting all of this together, let's have this function and then break it. So what does this code do? We have a some value, a buffer of 200 bytes, and we read the we ask it the user to enter the name. Then we say read that input from the user using getS. GetS also returns a pointer to the red string, which will be exactly the same as buff, but yeah. And then we will print out the whatever the user inputs, and end it with a new line for our convenience. So I should have that code somewhere here. Yes. This is the buffer vuln program, and can I make the text slightly larger still? This is exactly the code from the slide, because the slide imports this from this source file. So buffer vuln, please enter your name. Hello, my name is Tom. That works as expected. Let's give this thing some more interesting stuff. %p, 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 %p. Well, clearly we can start reading up the stack. Interestingly, we see here some value that looks like a thing, part of the program memory, perhaps. Actually, I am making a big mistake. What is the big mistake that I'm making? I've not disabled randomized addressing yet. So you'll see that the values are different this time around. You see here that there's these %p's and spaces that are appearing, which is what we expect, but these things are different every time. So let's bash, turn off the randomized addressing. And what we will do now is buffer vuln. %p, %p, %p. You'll see that it is the same every time. I'm getting a bit tired of repeating all of that stuff. So I will start writing a little bit of, let's do it with a shell program this time. Exploit buff.sh, and I will run it below there. Bin sh, buffer, no, exploit buff. I need to change the mode to allow it to execute. Well, that doesn't do anything yet, but that's expected. I want to get a string with a lot of %p's. For I in sequence from 0 to 100. Actually, let's make that a command line argument. Attack string is the empty string. Do that. Okay, this is a very simple bash loop and shell loop where we will just iterate over how many items and then just add a %p to a tag string every time. And we will give that to buffer vol. And it's not working. Why is this not working? Oh yeah, because I needed to give it a argument. That's much more like it. Let's also add a space. Well, that is crashing. Let's figure out when it crashes. Num parse I've here written a very short thingy that allows me to print the size of the input. So 337 is maybe a bit long. And 40, it doesn't crash. 124, it still doesn't crash. Or you can use buffer vol. We can, of course, have the source code so we can cheat and see that it's 200. So let's step up a bit to 50, 80, 244 is too much, 74, 226, 72, 70, 69, 68. Apparently 68 is more or less the magic number. Well, what do we see around there? There's a, this looks like some stack address. Oh, these are also stack addresses, and they follow the sequence of %p spaces. So that is interesting, because it could very well be that this is more or less the end of where we're going. There's this address, there's also some stack address, and then there's this value. So where are we? We add, I want to add an extra byte somewhere, because I want to get a more fine-grained control over when exactly it's crashing now. Tag string and a space. Okay, it's exactly 108 when it crashes, it seems. 208. Interesting. So when might this program actually crash? There is this red. No, that'll just go fine. Because this will be written correctly. It will crash whenever the frame pointer is incorrect. So what we could try to do is take this value and is this 1 second, I haven't put my tools on the correct place. Yes. Let's take the second argument, and so attack string is our %ps, and then we will add bin reverse address and then the second command line argument to our script. This means that I can now do 1, 2, 3, 4, and that crashes because that doesn't look like an address. Let's actually just give this value. Interesting. Where are we? I'm trying to figure out where it is writing right now. Actually, I want to do if second argument is not empty. Then do this, done. So I might be going slightly too quickly. So what is this piece of code doing? This will print however many %ps as I want. Then if I specify a second address, namely if this string is not empty, then it will, actually it's not correct, is empty, then we will use reverse address to take the second command line arguments to the script. The command line arguments to shell script are in 1, 2, 3, etc. and pass that to reverse address. Then we will compute here how many bytes there are in the attack string by printing it out to the word count command and having it count the number of characters. And then there is, we will give the string into buffer1. So I'm trying to figure out where it is writing. There is this address here, and if I add, go to 67, I'm an idiot again. This thing is being run on the wrong. I'm sorry. I forgot to turn off address randomization again. This happens. Uh, 68. I like to be safe, so I won't turn it off in my shell. Yeah, that's much more likely. See that we have this 70 appearing here. I expect that that's actually part of. It's not. That's actually a 70, not one of our percents. What happens if I do 100? Okay, something very interesting appeared. I just added a way too long string. That makes sure that I overwrite everything and that it will overwrite the buffer way too long. There is still this address here halfway through. Now, why is that? It turns out that if we look into buffer vuln.c, that getS is being called here. We will read the buffer and write it into buff. But what getS will do then after that is that it will return the address of buff for reasons, because getS returns a character pointer, and then it will write that to red. But if buffer has buffer will first overflow red, but then after that this address is written. So we now know that this is exactly the start of the buffer. So now all we need to do is put it in the right place. So 68, that's not the right place. Can we see where this thing is going? FFFFDA. I think I might need to add a little bit of padding. I will add a third command line argument, which then and this time I want to put just something in front of it. Fee. I can now see that I wrote the address here correctly. Because if I don't do that, you see that this is some other value. But I think I might need to add 8 more bytes to get to this value. So 9. Okay, why are you not working? I am not overwriting you correctly. Because I'm only doing this once. That's what I need. So what do we see here? I think I might be printing too much still. 65. Add a bunch of things. And I'm looking at these addresses. This is the frame pointer and this is the return address. If I look at this, I see that I'm partially overwriting the frame pointer. It starts with 7FFFFF, then we get a NullByte, and then we see 7FFFFF again. Why is that? Well, we're printing this to somewhere, and it's in little endian format, and it will end, because this is at the end of our output string, it will have a NullByte at the end of it. So that's that NullByte that we're seeing here, and that's exactly at the start. So if I add 8, you'll see that we've moved over that, and then 9, we'll see that we've perfectly overwritten that value again. Now, if I then add another 8, I think, what is happening? This does look correctly. Why is this not working as I want it to work? The joys in exploiting. Okay, I will admit that I should have prepared this demo better. I will just add another 8. 17 plus 8 is... Actually, what happens if we do 18? Then we will see that a space appears here. That is not what we want. 17. So 17 plus 8 is 25. And then I add another 8 is 33. What happens if I add another 8 is 41. You could see that the value that I'm writing is traveling through the stack. But I think I'm overwriting slightly too much here. And I'll need to quickly regroup what I'm doing. Let's break here and continue the adventures on the stack after the break, and that gives me a little bit of time to figure out what I'm doing again, and then go for the actual thing. See you at, what time is it? It's 22. We'll resume at 20. Seriously, my mouse has just disconnected from Bluetooth. We will resume in 10 minutes at, or 12 minutes at 16:35. Okay, it turns out that I was both doing it correctly and being an idiot. Let's reconstruct what I was doing. I have opened the thing in a debugger, but before I did that, I have exploit buff.sh. I've changed the shell script to just output the attack string as standard output, and this is now printed as standard to standard error to make sure that it doesn't interfere with that, because that will allow us to run GDB, GNU debugger, which can help us figure out what is going on. Let's do break on the function func. And then when we call run, it will stop there. We can do next. It will step through the program while we enter our name, and then it will print out that, and then eventually terminate. Now what we've done with the, by changing the shell script, we can now run it in and give it as input to the program. .sh. Yes, please. And now I've not given it input, but can also do 68. And then I can use the debugging functionalities of GDB, such as info locals, to see what the value is of buff. And I can see that printf info locals again. You can see that indeed red is a pointer to the %ps, and the %ps, etc. are in buffer. And info frame shows the stack frame, and that shows us that this is the return address, etc. Now, what happens if we give this this address? I could have sworn it was different just now when I tried this, and some other stuff. We now have a 222 character long string, info frame. This is our return address, frame pointer, and then we execute the get s, and then we do the frame again. You can see that I've now overwritten the thing with exactly the address that I've given. Apparently 8 was a very lucky guess of mine. It will now jump to that code, but what is at that address? A bunch of X's, which is obviously not actual shellcode. So I was doing it correctly, but I forgot a very important step, namely to actually insert the shellcode that I want. So I'll quickly go to this frame. I want to add this shellcode to my program, And let's use this to the shellcode program has also an optional argument, which is the number of NullBytes you want to actually additionally print. So if I do this and then type 10, it will start with a bunch of OX90s and then follow that with the shellcode. So that gives us a nice knob sled of 10 knob instructions. So integrating that, let's go open the exploit the shell script again. Then we now can provide how many %Ps we want. We add our address at the end, and we have this attack string. And we've seen here that 222 is the length of the input that we want. And then we want to have that address at the end. So I can go back to my run command, try this again, sure. That prints somewhat too many bytes. So we can reduce that 68, well, let's do 20, no, that's entirely too many, too few, 68, 40, sure, whatever. 170, that's too little, too few. 200, 55, 230. I could also do the maths, but I'm too lazy for that. And then it needs to be a bit shorter. Yes. Now, what will happen? Info frame, this is before reading the instruction. Then I will execute it via next and call info frame again. What we've now seen is we've overwritten this thing. Yes, we've overwritten the return address correctly, and for locals with the address of this thing, we can see here that our return, our shellcode is here, which is nice. That's exactly what we wanted. So if I now do next, 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 disassemble. This is the code that we were running, remember? No function contain, it doesn't want to do that if it's not part of the program. Boom. I pressed continue and we saw that it has executed bin ls. GDB tripped a little bit because we're no longer inside the program because we've inserted run code, but you can see that there is this code happening. We could do this without a knob sled because this was an exact address. But imagine we have only 60 again. How does that work? I think the thing got... apparently we've replaced the program that GDB is debugging. So we'll just quit. Let me do it the original way again. Oh, it's still open. And do that to buffer full. It crashes. Let's print only 50, that will work fine. You might have used that there is this other address here somewhere on the stack. That's probably close to where we want to go. oh, actually, this is the address that we want. This other address on somewhere else on the stack, this is some other stack variable. And it is indeed quite close to this one here. You could compute the difference between those. Echo. Nope. Okay. This program should allow me to do this, but it's compute the difference between those with Python, and it's 448 bytes. Okay, that's maybe a bit much. The AF is where we want to go. Let's reverse this. DBE0 is also quite close by, and then you subtract 20 or 30 or something, and then maybe you're already getting quite close. This is when the not sled usability kicks in, because you can then just subtract some amount of addresses and see what happens. Fortunately, because we in this example had this behavior where buffer vulnerability has this thing where getS is overwritten and the return address thus ends up on the stack, that we could read it a lot more easily. Not always that we are so lucky. Let me go back to my slides. So we've managed to break it. Actually, let me also do it for posterity with the correct thing. What was the numbers again? That is the address that we want, and then exploit buff.sh now with the shell version. I think I'm now in a shell in the program, but interesting. Yeah. We've opened a shell, but also immediately closed it again. So to get around that, I need to do a trick here, because the problem is that this thing attaches something to the standard input. So we need to attach another thing, which is this cut command, which we tell to read from standard input again, to reopen it, and then we can run the exploit again. Who am I? I'm Tom. Well, this is the actual shell that I've gotten now. You can see that I can type commands, and that this will work to do anything that we want. From print variables, try to read stuff like the users on my computer. That doesn't work. Screen. Now it does work. This works because I've now the difference with what we were doing is that if I go back to exploit my exploitation script, is that if you have this version of this command, then what happens is that because of the pipe, that's this vertical character, you take the input of buffer_vuln, standard input, and attach that to the output of attack string, and only attack the echo command specifically. And this echo command is something that just outputs something once and then it's done. So it closes the input. then what happens when we start up the shell is that it cannot reopen the input because it's still attached to the echo command output, even though echo is no longer there. So we have the use this construction with the parentheses and the semicolon and then the cut and then the line to have the shell do something for us, namely that it will concatenate these two outputs, these two processes, and take their output and then put them together, and then add it, give that as the input to buffer1. So cut with a line will have it read from there, and then it will output it again. So that will have it remain the input open and then pass it on to the bin_sh command that gets executed in the thing. Now we can go back to my slides for real. So a general plan of attack that we had was we needed to identify vulnerabilities. We did that by just, well, we had the source code, but if you just spam a bunch of %s's or %p's, you will see that it starts to print something else than the %p. Then you know that there is a format string vulnerability. If you get a crash when you give it 1,000 of things, you know that there's a get_s happening or a string copy. You will see a segmentation error. It usually indicates something is going wrong that you can use. Then you need to figure out how you can figure out what's going on in the other side. So if you're local, we can use GDB like we just did. When you're remote, you can use these %p's to see if you're overwriting where you want to be writing. Then if you get a buffer overflow when it crashes, is there maybe a return address there or a frame pointer? Next, you need to figure out what you want to achieve and how you're going to reach those goals. So if you want to just run another function, then you can take over the return address by finding that other function's address, then overwriting it, the return address with that address, or by injecting your own shellcode, for which there's these other two steps that you need to do. Of course, this example that I just did assumes that get_s is being used, and of course only idiots use get_s. It's deprecated, and hopefully nobody uses that anymore. But there's many other ways to shoot yourself in the foot. There's string copies. There are mem copies where you have the source length instead of the destination length. Strucat, strprintf, scanf are all functions that are problematic because they don't allow you to set any limits. Get working directory is a fun one. This will read the working directory that your program is in. So that's the same as the pwd shell command, but it will write that to a destination, and that destination does not have a size limit. Getwd will just, if you're in a very long path, do whatever it wants, and so on. There are also many DIY foot guns that people have made and sprinkled throughout their core code for people with malicious intentions to find. And yeah, the problem here more or less is that there is in C just no reliable or standardized way to determine the size of a buffer at runtime. That information is just erased at compile time. That means that a function that you're writing cannot detect if the pointer that they're getting points to a large enough amount of memory. That is annoying. So how do you prevent such buffer overflows? Well, a good way to start is to write and promote using safer functions that require the programmer to pass the length of all the buffers that are involved, so that you can check if you remain within those limits. String copy is a good example, but again, you need to make sure that destination is still null terminated if source was too big. Another way to construct functions, they are functions that will figure out how many memory they will need to store their result, then allocate that memory themselves, and then return a pointer. So that will put it on the heap. There are some performance implications there, but it will allow for a more ergonomic design where you can just know that the memory that you have is large enough. Another way to solve this problem is by using safer languages. For example, in Rust, my favorite pet language, the size of arrays is part of the type. So the type system, when type checking your program, will make sure that you cannot do operations on certain on arrays that go outside of the bounds of those arrays. You need to exactly specify how large something is at compile time to use an array, which is also sometimes annoying. But you can use these resizable buffers anywhere where the length may vary, and then you will get around many of the problems that might be with such restrictions. Alternatively, you can just keep track of the size of your buffers, store that alongside the buffers, and check that at runtime. So how do we make these attacks harder? I mean, it seems, although it took me an hour, it was not a very complicated attack. And the underlying principle that enables these attacks is that code is data. We put code on the stack in this buffer overflow attack. A solution to stop that from happening is to simply say to the operating system, this piece of memory, you cannot store code in there. If there's code in there, please refuse to execute it. This is a feature of CPUs that allow to set a bit flag on pages, so pieces of the memory, that mark it as no execute. This is also stuff that will be covered again in the operating systems course. But that bit set will turn our jump to a stack address into a segmentation error, because it will be the CPU will try to read from the program counter, which is then set to our stack address, and it will try to read a piece of memory that's marked as no execute, and then it will say, can't do this, please go away, and will say a segmentation error. This is often implemented as the principle of write XOR execute. So either write or execute, and never both at the same time. We turned this protection off for academic usage by saying using the -z execstack option in GCC, although you can also disable it on existing binaries. If you want to enable it because you've turned it off, you can also do that. But there are some programs that actually need executable stacks because they, for example, do self-modifying code or other weird things, but then you really maybe need to ask yourself if you need that. If getS would no longer exist, to respond to the question in the chat, then also some abuses go away. In fact, if you compile with a modern enough standard of the C standard, then your code will not compile if you use getS. It will just say a deprecated function does not exist anymore, and then it will crash. But the C language people are slightly fetishizing backwards compatibility. So they will never turn something off in the older standards of C, which means that getS will remain there. Although I would not be surprised if compilers will in the future at some point say, if you want getS, you will have to set these extra compiler flags to opt into unsafe behavior. But again, it's also way not the least of our problems. There are so many other ways to mess up that it's something that's very hard to really kill all of these problems. So another way to protect your programs is to use something that's called stack canaries. It's after the idea of the canary. In a coal mine, people would take small cages with cute fluffy birds in them, which would make nice musical sounds, and take them down into the darkness of the coal mine, and then they would go away working in the mine, keeping the bird with them, and then if the chirping would suddenly stop, then they would run and get the hell out of there, because birds are very sensitive to toxic gases, and they would know that there is a risk to their health in that mine. Very sad for the birdies, of course, but these stack canaries are just a bunch of bytes, so we can kill a bunch of them a lot less scrupulously. The canaries in the stack work in the following way. So we have a canary value that we put somewhere on top of the stack frame, and then we have all the buffer overflow stuff, the sensitive stuff, the stuff that breaks somewhere below the canary. And then at the end of the function, you will check if your canary is still the same as what you initially set. The solution, the idea here is that if you do this buffer overflow, if you want to overwrite the stack addresses, the return address, the frame pointer, they need to go through the canary. So before we return, we will check this canary, and then if it's no longer what it's supposed to be, then we know that the frame pointer is no longer to be trusted, the return addresses are no longer to be trusted, and we will just terminate. We will not try to recover or anything because something fishy is going on, we'll just stop. So doing this for every function might be a little bit annoying, but fortunately there's something called a compiler that can just do all of that for you automatically. There's the fstack protector feature that's turned on in GCC and client by default nowadays, and that will do this, precisely this for functions that have certain features. You can turn it off for educative purposes, for example, if you by setting fno stack protector, and that will just then disable this behavior. The example I just showed you had both an executable stack and the stack canaries turned off. But these canaries also need to know some tricks. They need to be smart birdies. What if we just use a fixed value every time? Some constant that we define at the when we compile it, some hard-coded somewhere in a program. Well, what we could then just do is overwrite the canary with its own value, because that value doesn't change. We can just reuse it every time, and we can then, as an attacker, we know what needs to be there, so we can make sure that it is there and then overwrite it. So to get around that, you need to make sure that it's randomized every time. Then if you want to exploit it, you would first need to read it before you can overwrite it with its own value. So that will mean that you need a much more advanced attack. For example, you need 2 vulnerabilities instead of just 1 before you can overwrite the canary. Another trick that is fun to use is to put a NullByte in there. Because NullBytes terminate strings, that immediately stops any string injection attack from overwriting what's behind the canary if you intend to preserve the canary. Because if you want to preserve the canary, you need to overwrite it with itself. But if there's a NullByte in there, you cannot write anything beyond the NullByte if it's a string injection attack. If you want to bypass that, you would, for example, need 2 string buffer overflows, because you would first have to overflow all the way to the return address, and then you would need to overflow it up until the NullByte in the canary to set it back correctly. which also again makes attacks that much more complicated. But these are all mitigations. There's more things that you can do to make stuff more complicated. We will talk about defeating write or execute next week. But you might ask yourself at this moment, why do you bother anyway if you can defeat it? Well, not all attacks are by some 3 or 4 letter security agencies that have a lot of money. These mitigations, they all keep out also the less motivated attackers, a script kiddie in the basement, or some things that don't have the time and effort to put in more sophisticated attacks. They will need to either find bigger holes in your program or squeeze a much more complicated hole attack through a much smaller hole, and thus you gain some protection. They also often make a lot of attacks much less reliable, which is very important for stuff like automated attacking, and harder to execute remotely because you cannot really figure out what's going on the other end if it crashes half the time because of these protection values settings. All of these things more or less just increase the monetary cost of an attack. Of course, not everyone is motivated by money, but still, for a lot of people, either they're paying someone to break something if you're a criminal or a 3 or 4 letter agency, or time is still money, of course, so that helps. Because most people don't need to really worry about the NSA or the NSA's budget. If you want infinite security, you will need infinite money because there's always something to improve, to make safer, etc. And that will go on forever. You just need to make it safe enough so that people just go for some other target most of the time. So wrapping up what we did today, we took control of the return address to jump to code that we put in the program, for which I will repeat that it helps if you put the code in the program. The code that we put there was the machine code that launches a shell. Again, you don't need to know that for the exam, but for the shellcode, we need to be very careful to avoid these NullBytes. We used the printf to find some return address and the addresses of local variables, and we used it to figure out the number of bytes we needed to write to overwrite the return address. We talked about knob sleds to overcome this addressing uncertainty, and we talked about some of the mitigations that exist that make attacks much harder to execute. Write or execute, XOR execute, stack canaries, and next week we'll also cover ASLR, which is address space layout randomization, that annoying thing that we have turned off every time. And we will wrap up with that getS is terribly unsafe. Okay, I now have some things on the homework. The exercise 3 of last week has a small thingy if you compile it with a modern compiler. So you might see that you get launching shell, which is the desired output, because then you've executed the attack correctly. And then you will get this seg fault, and this seg fault actually then happens in one of the system files. So POSIX system.c and do system, clearly no longer part of your program. What is going on there is that the system calls require a 16-byte aligned stack pointer. That means that the stack pointer needs to be divisible by 16. There's some ways to work around that. If you have run this attack in GDB, you could just make sure that the stack pointer works before jumping to the shell, to the launch shell function. But that is slightly hard and annoying, and doing it without GDB is very hard, almost impossible. Definitely not within the scope of this assignment. So if this happens to you, that you do get launching shell, that's important, but then it crashes in system.c. basically see green text, but then it crashes, then you can just hand it in as if it had worked. Say, okay, it crashed and was being annoying. I think it's because of my compiler. Too bad. But I did overflow it correctly because it executed launching shell. So you can still answer all of the questions that you might that might be asked. Yeah, I think that would cover that. Then there are some things that I would like to say about the exam. I have opened the thingy. I have built a new website, and this website is a very special website where you will be taking the exam on. I say exam because that's the technical term for a graded piece of work. It will be not something that's within 2 hours. You will have a week, I think, to do a bunch of challenges. So I'm already logged in. You will see some windows, some cards like these, where it says that there's a description of something, and there will be others here, and then you can complete those, and then you will be graded based on what you will write up. So there's these challenges. There's a description here, and then there's this flag submitting thing. And the goal in all of the challenges is to obtain a flag. It's this type of contest, competition, challenge is called a capture the flag, where the idea is that you need to break something and to obtain the solution. These flags will be randomized, so every one of you will have their own thing. And I can click this button here to start this assignment. It will now launch a bunch of containers. And it tells me now that these are the instructions that I can use to connect to this challenge. So if I go back to my terminal, I can now paste that, and I'll see that they will get the solution to this exercise already. Of course, this one was beyond trivial. So then you can submit the flag, and then you solved the challenge. But that's not what you will be graded on. I should be very careful to say that. The idea here is that you will now write up something about your challenge. Summary. It was easy because the example already gave me the flag. Expected look oh. Good point. Stupid. There. Code looks pretty probably like, and then you can add a while true. And then you can see that you can submit your write-up here. It saves it automatically. And then you can will automatically submit all of this stuff. It's slightly, the delay has seemed to have gotten longer, which was a bit off-putting. So we've pasted this flag in the submit button, and it was correct. I have typed a little bit here. This thing does markdown. I've made it. This website is all new code. Took me quite a bit of time to write, but it will allow you to submit a write-up here. There will be a lot more guidance on what exactly we're expecting from you to follow, but you will probably already get to play with this a little bit in this week's homework. You see now that I've completed this challenge, some statistics, and there might also be, there will be more challenges posted on this whole system, and I get to have a whole admin interface where I can see what everyone did. The challenges will be a bit like the homework exercises and some things that are variants of those. There is the probably going to be some buffer overflow, something with printf where you need to dump part of a memory, stuff like that. I haven't written all of them yet, but I should emphasize really that you'll be graded not so much on getting it done, because that also gives me very little information to grade you on, but on the write-up. So I want you to write about how did I start, what did I see, what did I assume about the code, what did I use to break it, etc. And that will allow you to get points even if you don't manage to get the entire exercise done. Yeah, that was that. I think that works out for time very well. What did I have something else I wanted to say? What did I promise in the Brightspace announcements? Nope. Someone asked me to go into knob sleds a little bit more, so I will go back to my slides and explain that for those who want to see it. For those who don't, I can already say see you not next week, because next week is a holiday again. It is really holiday season this quarter, but we will see each other again in 2 weeks. The details on what you need to write, etc., will all follow. That will definitely be given more examples of, etc. If you use GNOME terminal, you can use Ctrl-Shift-C and Ctrl-Shift-V to copy stuff, by the way. Okay, so knob sleds. The idea is that you have this instruction that does nothing to give you some room before you have the shellcode. This gives you this margin of error, because instead of having to exactly jump at this place, you can just jump in any of these places before it, and then you give this margin of error. A knob sled. The function that we had is a good example to do such an attack. Clear, please. Of course, this program already did the entire thing I reconstructed. Let me figure out how this program works again. Wants to have how many %Ps I want, then perhaps an address, and then perhaps the number of knobs that I need. I definitely did steal someone's picture for the example. So let's take 50 of these and give them to buffer von. So let's assume for this moment that I'm blind and did not see this. I might have this address though, which seems to be somewhere on the stack in the vicinity, that I might try to base our attack off. So if I take this and subtract and then 100. Actually, I know that the size of the buffer is at least 200, so let's do 200 and subtract 200 bytes. So this is the approximate address that we're going to use to do the attack. We're going to try to jump into there and now we need to figure out, I need to fix my, where's the Python 3.7? Hold on for technical difficulties. It's the Python version of that script. So I have some stuff, and I want to probably overwrite this thing with our return address that we had there. We're still quite a ways off, so I can start writing some shellcode. And what we'll see here is that if I pipe this to the hex dump, that we'll see that we have now one NullByte, then our shellcode, and then a bunch of %p's. Because what does our script do again? Shellcode buffer, it will use the first one argument to define how many %p's we want. The second argument is given as the address that we want to reverse. And then if I give it third argument, that was the one, it specifies how many knobs I want and if I want a shellcode. So I could also write this, and then I will not get any knobs, or if I specify 10, then we'll get a bunch of knobs, and then you'll see that this piece of code starts with a bunch of these knobs. Now, buffer vol again. We have the input, knob. Then we see here parts of our shellcode. And I see here that the return address is still in the place where it is. Let's go for 20. I'm partially overwriting the frame pointer here, and that's why it crashes. Can add another 10 bytes. 30 adds another 10 bytes. And we can see here that I am now partially overwriting the return address. You see, namely 55555, then a NullByte 7FFFFF, which is what we need. There's 1, 2, 3 bytes that we probably still need to add. So if I add 3, boom, we've broken it. We know that this was not the exact address that we needed to have, because this happens to exactly be the address of the shellcode. Where the shellcode starts. This is F0, and this address that we have here is only 16 bytes in, 15 bytes further. But I could also F, so subtracting means that it is B1, 0, and it'll still work because that's all still in the knob sled. And you can see that 1, 4. You can see that this is all still being overwritten correctly here. So this allows us to use this knob sled to exploit the attack more carefully, less carefully. It's a good question if I could just use, say, these %p's are very nice to figure out how much I want, but I could also do it without any %p's, if not for some technical detail of this particular program. So if I, let's see, just use one, then we need 34 bytes. So I need to print 188, 89, and then we'll see that it still crashes. Why is that? Let's run GDB, and we'll quickly store these. Yeah, it's fine. GDB and then buffer vol, a break on function, and then we want to run it, and I want to give it as input exploit shellcode buffer.sh 0 some address, and we'll see what happens. Get s and then info frame. That is not the correct return address, so let's try that again. 80 info frame. Okay, that's slightly more of what we want, so I need to subtract a bit more bytes. Next, info frame. That's not the full address that we were inserting, so I need to add one more byte, which matches that this needed to be 122, of course. So 83, yes please, next, info frame. Was that the address that I was injecting? Indeed, and I can also try to print it. UU is a bit short. Info locals. Yeah. If you run a program in GDB, all the addresses move around a little bit because the environment variables are different. So I will need to do this again with the correct address. Info frame. Clearly I am, this address has a big downside. It ends in NullBytes. So I will need to, I can just add one. There should be knobs there. Okay, so this return address that we got should be correct. That's not what I wanted. We'll see that it's a bunch of shellcode. Oh, that's not. And that it ends in the bin sh stuff. That seems more or less correct, so let's continue. Illegal instruction. Okay, so what happened there? The problem was that, how do I print this as hex 200? Yes. We have our code here, and part of the problem is that, can I format this more nicely? I cannot. So I know what is going on, but I'm struggling a little bit with showing you. nop, 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 nop. And then we have that here starts our shellcode. And then our shellcode continues, and then we see that halfway through, we suddenly see an address appear. We see here that we have 7F, FF, FF, DA, OO. What is that address? Well, info locals says that we don't have any locals. Interesting. The problem here was that's of course the address where our thing was at. And that happens because if I go to, yes, please quit. Is that this get s reads in our knobs at the start, puts all of the knobs in here and then overwrites everything, and then we have the shellcode. But the problem is that this return address thing gets overwritten, overwrites part of our shellcode and part of our knob sled, and it will result in a big crash. Because this will include a NullByte, which is not what we want, and we will see that it doesn't get executed correctly anymore because the instructions get overwritten by this address red. Because what happens is we first overwrite buff and then we overwrite red with the correct value. So this gets trashed partially. So that's why we needed some padding at the end, which was very convenient in the original version, is that these percent P's that we have here and the spaces, you also see that they get overwritten here by the value of the buffer, the value of red. You can see that there's percent P's before and after it, so that means that this got set later than the get s did, which means that that's why it will crash if we just do it without any percent P's. It could be anything but other than percent P's. I mean, I could also use spaces here, double space, triple space, and then it should still work. What is going on? Interesting. Space, or let's just do something else, XXX. Yeah, there it goes. I could just do something else here, but then we just need to have something behind the shellcode that can get clobbered. So it's nice to keep the shellcode inside the legal buffer so it stays okay. And yeah, with that, I don't think I can go over this in much more detail. I would suggest you go to webcam. That YouTube is also a good place to find many tutorials for this. I think that if you go to youtube.com and then search for why is my internet being slow? It must be because I'm streaming to a bunch of people. Sled. Then the computer file is known to do sort of nice videos, I guess. Someone going on a whiteboard with this, knob sleds return to libc, that's next week. Someone who has very nice intro page thing, I do it in front of a blackboard. There's many resources to use here. But the final thing I think I will say about knob sleds is that indeed you want to squeeze in as many knobs as you can get away with, but you also need to be careful that your buffer overflow code, your shellcode, the stuff that's going to be doing your work for you, is not destroyed. So that's why it's also nice to have some padding at the end and not just at the beginning. In the past, if you had a 32-bit processor, all of these addresses were only 4 bytes. So what you would typically do is you would write your knobs and then your shellcode, and then your guest address, but you could just spam that address a whole bunch of time, and then that would also give you your padding. With the 64-bit addresses that have these NullBytes in them, you need to be a lot more careful because you can only print an address once, which makes it slightly more tricky to massage it into the right direction. But yeah, that's also why you sometimes still see a bunch of these tutorial videos using 32-bit examples, because it's just so much easier to exploit. With that, I think I will wrap it up for this week. There will be a regular tutorial tomorrow. You will probably already have seen that I sent an announcement around that postpones the deadline. So you won't have to hand it in tomorrow, but you'll have to hand it in on Thursday. It's still at 12:30, so we can distribute everything in the afternoon. We hope that gives you a little bit of extra time. And also I think that me going through the exploit here with GDB shows you a little bit of what things you could do, especially info locals is a very useful command. Info frame as well. Yeah, with that, I think I will wrap it up for this week. I will not see you next Monday, but you'll see me. I guess I won't see you anyway, but you'll see me again on the last week. So that is on the 8th of June, and that lecture will be mainly some background stuff, not anything you'll need for the exam, but it will be wrapping up on countermeasures, getting around some of those countermeasures, and I'll probably have a lot better idea of what the exam is going to look like exactly by then. Have a good evening, enjoy your dinner if you're going to have dinner soon, and I need to start cooking. Bye.